Hi, I'm Stephen, and this is a video series on classical mechanics. Alright, let's start with a story. 1 year from now, I want to buy my first car. Most of that money will come from selling beer. Right now, I have 300 cans of Heineken in my room, and a group of underage friends who will pay anywhere up to $10 for one can. If I charge $9, I will sell one can a day. If I charge $8, I will sell 2. In general, I will sell 10 minus price beers per day. All of this money goes into my bank account, which earns 5% interest, compounding. How can I maximize my takings? Well, if my stockpile on day T is Q of T, I need to pick a pricing strategy that optimally spaces out my sale of 300 beers over 365 days. I sell negative Q dot beers on day T for a price of 10 plus Q dot per can. Q goes from 300 to 0 as T goes from 0 to 365. So at 5% interest, this is the present value of all my takings. I hope you can see I'm torn in two ways. On the one hand, I want to sell beers at a steady rate to get a good price. It wouldn't make sense to quickly lose my stockpile at a discount. On the other hand, 5% interest is a huge incentive to try and collect more at the beginning. This type of problem is called calculus of variations. A functional is a mathematical object that forms a number from a function, q. Here, s forms a number out of q by integrating from 0 to t this curly L, which depends on q and q dot, and possibly time as well. So how can I maximize or minimize S? By choosing the best possible Q of T. In high school you learned about static optimization. To maximize or minimize a function, say S of Q, means you can't get a better result by choosing a different value, say Q plus epsilon or Q minus epsilon. The only way this is true, of all epsilon, including positive epsilon, infinitesimally shrinking to 0, was if ds dq equals 0. The idea here is very similar. Suppose I've truly found the optimal function, call it q star, and compare it against a different choice, say q star plus k epsilon of t. For any positive k and function epsilon, this result is either the same or worse. Bring this across, divide both sides by k. Likewise, the outcome using k star minus k epsilon of t is also either the same or worse. Bring that across, divide by positive k. If I can pick any positive k I like, what if I shrink it to a small positive number? In the limit, these two things equal ds dk at k equals 0. But if this derivative can't be greater than 0, and it can't be less than 0, then it must be 0. If we were trying to minimize rather than maximize S, both of these inequations would reverse, but we would reach the same conclusion. ds dk equals 0 at k equals 0. Alright, so what is this derivative anyway? It depends on the functions, q star and epsilon. Remember that S is the integral of curly L. Differentiating under the integration symbol, we have dl dk equals dl dq times the change in q, and dl dq dot times the change in q dot. But if q is q star plus k epsilon, dq dk is just epsilon. Likewise, the change in q dot is epsilon dot. Evaluate at k equals 0, so q is just q star. So there you have it. We need to find a function q star such that this thing equals 0 regardless of what we pick for epsilon. Alright, how do we do that? There's a trick. If you integrate by parts, you produce a boundary term and a term where epsilon factors out quite nicely. Epsilon at one time point is independent of all other time points. So if we want this to vanish for all epsilon, this bracketed term, called the Euler-Lagrange derivative, must vanish at all times. This gives us the Euler-Lagrange equation. The start and end values of epsilon might also vary independently. So, dl dq dot at the start and end vanish. We call this the transversality condition. Our current problem has two Dirichlet boundaries. Our current problem has two Dirichlet boundaries because Q must start on 300 Baires and end on 0, and so the variation epsilon must begin and end on 0. The fact that epsilon of 0 and t both vanish allows us to forego the transversality condition. You might wonder why I started this video series on such an obscure problem. I wanted to illustrate the Euler-Lagrange equation because this type of dynamic optimization is the language of the least action principle, which is the heart of classical physics. A functional may not necessarily have an optimal input or extremum, but if it does, we have proven that it must satisfy Euler-Lagrange, a second-order differential equation with either prescribed Dirichlet boundaries or the transversality conditions. So in my little story, dl dq dot equals 10 plus 2 q dot e to the negative rt, where r is the daily interest rate. So dl dq is just 0, and we have a linear second-order differential equation with constant coefficients. These lambdas represent solutions to the characteristic polynomial. There is just one choice of constants, a and b, that satisfy the boundary conditions. If I want, I can substitute this answer back into the original functional to find out how much cash all that bear is worth. In general, dl dq dot varies with t, q, and q dot. Therefore, its derivative in the Euler-Lagrange equation accounts for all of these dependencies, so we get these three types of terms. There are more complicated problems where we are free to pick two functions, let's call them q1 and q2, to optimize the integral of the Lagrangian. That depends on both q1 and q dot and q1 and q2 and their derivatives, and possibly time. We can repeat our argument to show that q1 must satisfy this Euler-Lagrange equation if it is truly optimal, and that q2 must satisfy its own Euler-Lagrange equation. There may not exist an optimal pair, for example, a trivial problem that permits, say, arbitrarily high or low outcomes. But any solution that does exist, if there is an optimal pair, must satisfy the Euler-Lagrange equations, both of them. When we expand out these total derivatives, we must account for the time dependencies that occur through q1, q2, q1 dot, and q2 dot, as well as direct time dependencies. We can conveniently represent this vector equation with dl dq on the left, and on the right we have a matrix of second derivatives in q dot times q double dot, and matrix of second partials over q dot and q times this vector of q dots, and this vector of explicit time derivatives. So what does this story have to do with classical mechanics? We're going to revisit the Euler-Lagrange equation again and again and again, because a function that extremizes this type of dynamic optimization problem will necessarily solve Euler-Lagrange, and we'll see why that's important in the next video when I talk about the least action principle.